Okay, let's see here. Yeah, we're recording. Okay, good. So, picking up where we left off last time, starting with a quick kind of reminder of the context that we had sort of set up last time. We're going to talk about something called Gauss's divergence theorem, which is a lot like Green's theorem, different in its ways, appropriate to the different context, of course. Totally different context, so totally different details. But structurally, it's pretty much the same. So we're talking about three-dimensional solids and their boundary surfaces. And we have a convention now on what we mean by an orientation when we say the boundary of a solid. Keep in mind the word boundary, loaded word, right? The word boundary now specifically implies a specific orientation. Just like Green's theorem, we're ultimately talking about an accumulating quantity. We're integrating an accumulating quantity. So different details, different contexts, of course, right? But here we're going to be talking about boundary flux as our accumulating quantity. That's the stuff. That's what this is really about. This theorem is going to be about boundary flux. And as we discussed, nice little picture you can draw to persuade yourself that, in fact, boundary flux is an accumulating quantity. To be more precise, it accumulates over the solid, right? Very importantly, accumulates over the solid. It's the solid that if you cut it in half, the boundary flux of the left and the boundary flux of the right gives you the boundary of the whole solid. Okay. All right. As we've discussed previously, and I'm actually not even sure why I have these sections of page, these slides about this, because it's really, truly a point we've already made. Any accumulating quantity can be thought of as being a local quantity, even if it's thought of globally. It can be thought of also as local because of the fact that it's accumulating, because I can chop the solid up into pieces and look at each individual solid. So any accumulating quantity, you can view it as behaving kind of like stuff, which I choose because it sounds vaguely physical and yet it's general and generic, right? But it does. It behaves like stuff. And as such, it makes sense to talk about how much of that stuff is there on any given little region, and that is per unit size, in this case volume of that region, and as such we get an associated density. So flux density is going to be the tool that we're going to use to compute the accumulating quantity of flux. Just like mass density is the density that we use to compute the accumulating quantity called mass, right? It's the same, structurally, same thing. Okay, so again, details go into showing that this is the formula for that flux density. This, by the way, is why we cared about divergence, denoted in either of these ways, as previously discussed in Chapter 3. This is why we care about divergence. This is why it was discussed in Chapter 3, is because it's going to be the thing that it's going to be our integrand for our integral. It's the density of our accumulating quantity. It's flux per unit volume. Okay. All right. Again, we went through all these details last time, but, any accumulating quantity you can think of as being kind of local, like mass. Could be distributed over a three-dimensional region, but you can always talk about how much is in some little vicinity. And, of course, density is what tells us in some sense how much mass is there going on kind of in this general area as opposed to in this general vicinity over here. So likewise, flux density is the thing that arbitrates the analogous question for flux. If you want to know, given a certain total flux, if you want to know how much is coming from either of 2 points, compute the divergence of those 2 points. Okay. All right, and I believe this is about where we ended it, so I'll repeat this a little bit more slowly. So, summarizing what the tools that we have that we're putting together now. Flux you can think of as being an expression computed from other fundamental things like a vector field, right? But you can also choose to think of it as itself being a fundamental quantity. You can think of flux as being the stuff that we're interested in. When you think of it in that way, it is an accumulating quantity. That's a big point. That's a really deep point. Ultimately, this is one of the cornerstone things that makes this whole argument hold together is the fact that it's accumulating. And as with any accumulating quantity, you can talk about, for any given piece, spread over any given corresponding volume, you can talk about the associated density. And again, that's what divergence is. So I do think it's a really helpful compare and contrast to recall, if you look back in the section on Green's theorem, the way I sort of put the pieces together when we were talking about Green's theorem, I deliberately have laid this out to be totally analogous. So they'll look kind of the same on the page as you're looking back and forth. There's a quantity in question that we establish accumulates, for which we identify, skip the details, what the formula is for the associated density, and then we're in business. And note in particular here, we have a new theorem that says that outward-oriented boundary flux can be computed as a triple integral over the interior, integrand being divergence, aka flux density. And so there we have Gauss's divergence theorem. Let me take a breath, give you all a chance to squeeze in a question if you have one. Anybody? Everybody's all right? Okay. All right. So let's see an example. Okay, so again, here's the question, and note nothing in this question says use Gauss's divergence theorem to compute a certain flux. The question just says compute the flux, right? So y'all have to kind of start to insert in your mental processes this, hey, wait a minute, how should I approach this problem? Which of my several tools should I use to answer this question, right? Now, at a quick glance, you could, I suppose, take a kind of a plug and chug, parameterize the sphere and plug in the vector field, pull back through the parameterization and all that jazz, right? You could totally do that. I really don't advise it, right? On this example, that would be a nightmare of ugliness. For example, keep in mind, when you parameterize the unit sphere, x, y, and z get chock full of trig. So lots of trig cubed, yikes. Lots of trig in an exponential, right? Lots of trig. It's a nightmare if you run at this head on. If you try to pull back through the parameterization. Impractical. I don't want to say it can't be done, but I don't want to do it, that's for sure. Okay. So, different approach. We have a brand new shiny theorem. Oh, here it is. Brand new shiny theorem that says, hey, if you want to compute a flux, how about you just compute the corresponding triple integral? So we would like to use this theorem. Now, there is a catch, as with all of these accumulation theorems, which I sometimes call boundary theorems. The catch, as there is with all of them, in this case, is the fact that this can't just be any flux. This has to be very specifically a boundary flux. If you look back at the argument, the fact that this is a boundary is essential to making the argument work. The whole thing, you can't even start the argument until you've established that we're only talking about boundary fluxes. Right? Very, very important. And again, not just an academic point. This isn't just a matter of the formality of technically it has to be continuously differentiable or something like that. No, you need it to be a boundary because there needs to be something that is a boundary of, because that thing that it is a boundary of is the domain for your triple integral. If your surface is not computed over, if your flux that you're interested in is not being done over a boundary, there is no triple integral. It's not that, oh, well, yeah, technically in this case, the triple integral and the flux don't happen to equal. No, there is no triple integral because there is no domain for it to be defined on. Does that make sense to everybody? Okay. You really got to watch out for this. It's a very dangerous scenario. So we have to look now at our question. We want to compute this flux. Flux is being computed over the, let's see here, it is the inward-oriented unit sphere. Is that a boundary? And I'm sorry to report that no, it is not. Right? Orientations matter. This is a big deal. This is not a sign error situation. This is a very significant, sophisticated, deep point. Right? So, as written, the surface is not a boundary. You can kind of see it right here. I mean, our surface, again, it's inward-oriented unit sphere, and so let me highlight just kind of part of the sphere there, but inward-oriented, that's not how boundaries work. Now, there is a closely related surface, same underlying surface, but this time oriented outward, oriented in the opposite direction, thus the little notation here with the little minus in the superscript, right? Very closely related surface. They're the same surface, minus the orientations. Right? And this one is a boundary. Right? So to the green surface, we can apply Gauss's divergence theorem. To the blue one, we cannot. So, yeah, cool, no problem. All we have to do is just say, okay, fine, you want to compute the flux over the blue surface? Well, it's going to be the negative of the flux over the green surface. Make that first observation. And now, the thing we're interested in that we can't use the divergence theorem for, I have conveniently related to how it relates to something that I can use the divergence theorem for. Does everybody see how that happened? All right. Okay, so with that noted, the rest of my computation, I kind of don't even really need the blue surface anymore. All I need is to keep the minus sign, of course, right? But just recognize that I'm now going to be computing a flux over this new green surface, which is a boundary. And when you have a boundary flux, you can use Gauss's theorem and rewrite that as a triple integral divergence. Everybody on board? Okay. All right. It's all over with the details at this point. Of course, details matter. Computing the divergence is pretty straightforward, but the divergence ends up being 3 plus x, and keep in mind that comes from applying, the appropriate formula to this vector field right here. So we take the x partial of this, which of course gives me the 3, and then I need the y partial of that, which gives me the x, and then I need the z partial of that, which gives me nothing. So easy computation, but just for the sake of having said it, do make sure that you know the formula for divergence. It's essential to have that ready to go. Okay. All right. And so, now we find ourselves with a triple integral. And this is a triple integral over a ball. Quick reminder, don't forget that minus sign. It is part of what we actually care about. So how are we going to compute this triple integral? We're always looking for freebies. We're always looking for easy, sort of clever, smart alecky kind of ways out without having to do a bunch of work. Maybe this function 3 plus x, maybe that's symmetric. Right? Maybe it has an odd symmetry that coincides with a symmetry of the ball, but no, it doesn't. Maybe it's a constant. No, it's not. Right? There would be a couple of nice things that would make this triple integral really easy if only the integrand would cooperate, but it doesn't. Right? So the neat trick is to take it and break it up into 2 separate integrals. Right? There's the integral of the 3 term, and then there's the integral of the x term, And each of these is convenient by a different trick. 3 is constant, so this becomes just 3 times the volume. X does have an odd symmetry through a plane that is also a symmetry of the domain, the unit ball. So this is 0 by symmetry. This one is easy arithmetic. Everybody on board? So this example is kind of a dual-purpose example. It's an example of how to use the divergence theorem. It's also an example of a real cool integration move that you should always be on the lookout for. Everybody all right? Okay. Let's see. It occurs to me now to show you another example. Let's see, where did it go? Yeah, here it is. I'm sorry, I just scrolled right past it. Another example of how you can get in trouble if you don't pay attention to the fact that this has to be a boundary. Let's suppose that you're being asked to compute a flux. Compute the flux through some surface P, F dot ds. Right, this is the question you face, and this P. Let's suppose that it's like a piece of paper, right? So it's a rectangular shaped, part of a plane sitting up in space, something like that. Okay. So here's the tragic mistake that I see students make sometimes. You might even see this coming. What students can do is say, all right, well, domains, let's not worry about that. But we're computing a flux, and Gauss's theorem says that that's a triple integral of divergence. Now, let's suppose, as backstory, that maybe it's not given but easily computed that the divergence is 0. Let's just say. So a student writes down, well, it was a flux, so it's triple integral of divergence, which is 0, and then the student confidently says this integral is 0, so it seems. And I better put a question mark here, indicating that this is, in question. This is garbage. You see how tempting it is, though, right? The question was about a flux. Gauss's theorem is about a flux. It really seems like I should be able to just say triple integral of divergence. But this first statement right here is not only not true, it's 100% garbage. There is no triple integral at all. So it's another landmine, right? This is an unavoidable, this is intrinsic to the material, landmine, easy to step on. Right, so please make sure that you don't step on this one and don't actually do this, because the student who writes this down, nothing that's been written down is in the right direction. It's just not. So very dangerous from a points point of view. Is everybody comfortable in the morning here? Yeah. Mm-hmm.
I'm not sure I understand why that's not viable.
Yeah.
Is it because you're missing the in-between steps written down?
No. This isn't a matter of sort of a clarity. It's that, the presumption of my question here is that this surface, this P that we're looking at the flux through, is like a piece of paper, something like this, and it's not a boundary. Right? So Gauss's theorem does not say that you can compute any flux in the world with Gauss's theorem. Absolutely not. That's a gross overinterpretation. It's just dramatically wrong. And does that make sense?
Yeah.
So what the student is doing is ignoring a really important point and kind of sweeping it under the rug by not indicating a domain, right? Which, I do that sometimes, right? It's a convenience, right? But this is a sloppiness that stings because it allows the student to mistakenly think that this might make sense, which it just doesn't. Is that satisfying?
Yeah.
Okay. Everybody else? Yeah.
How would you calculate that?
Oh, well, yeah, there's other tools that we'd have to work with. You could parameterize the surface. There actually is another really cool method that I'm going to show you all later on called surface independence that is kind of like path independence. And there's a lot that we have to cover between now and then. But there will be another method there as well. Yeah. But this, all garbage. So make sure that's not you, really. If you're not clear on what I'm talking about here, come to office hours. Let's straighten it out. I want to make sure everybody sidesteps that landmine. Okay. All righty. Moving along. So I want to talk about some physical examples. Let's see here. I can go ahead and do that for one thing. The engineering school, I think this is an appropriate time to mention, is extremely interested in engineering students being comfortable with Gauss's divergence theorem. It's on their top 2 list of most important theorems in this subject. And the reason why is because it shows up in a lot of natural physical ways, and I'm just going to show you a couple of them. 4 of them, I guess. Arguably my favorite one is the light bulb example. So let's consider how light bulbs work in the simplest of senses. The light bulb has a bright spot in the middle. That's where the little LED is. Right? I like to work with LEDs because otherwise I have to draw a filament and it gets weird. Right? But little LED right there in the middle. And what does an LED do? Well, it shoots out photons every which way, right? And so that creates a flow field kind of like this. Now, one thing you're going to notice about how I've drawn this is that the field lines are stronger, but longer, greater magnitude, close in, but they start to get shorter, less magnitude as you go away. And why would that be? Because in this case, the natural way to describe this flow is not with velocity. Natural way to describe this flow is with density times velocity. Because we're going to be interested not in the volume of photons that pass through a given surface. We're interested in the quantity, right? Kind of like, if you're talking about a fluid, we're interested more in the mass per unit time, not the volume per unit time. So density times velocity is what we're interested in. And, of course, the density of photons is a lot greater when you're near the light bulb. Does that make sense? Okay. So there's our field. And now we could write down formulas and do a bunch of algebra, but I think that's a good investment of time, although it's a healthy exercise for everybody to do on their own at some point. What you would find, though, is that everywhere away from where the bulb is, so let's see here if I can, everywhere except where the bulb is, the divergence is 0. Now, again, that's if you can write down the formula for this vector field. I'll show it to you in a few minutes. You can write down the exact vector field. You can compute the divergence, and you will find that it is just flat 0. Okay. And, by the way, I claim that that's physically satisfying in the following sense. If you think about some surface hanging out over here, let's say about right... I wanted to be in the pencil mode. Some little surface about right here, let's say. Let's think about flux going through that little closed surface. Well, there's photons shooting through that surface all the time. There's a light bulb right here. Lots of photons. But the thing about it is, every single photon that shoots in also shoots out. So the inward flux on the bright side and the outward flux on the dark side, they match up. They're exact opposites of each other. Grand total, the flux is 0. That actually kind of makes it. The divergence should be 0 because all the fluxes around here are 0. Does that make sense? Okay, but if you were to compute what is the divergence at, let's see, I've already got this colored orange, at where, oh gosh, I didn't want the pencil, sorry. At where the bulb is, we've computed that, we've already established that that's where the photons are coming from. If you were to compute the divergence, it'd be massive, really, really big. And that, too, I claim makes sense, because if you're talking about flux per unit volume, and if we look, at this, let's look at a little small region containing the LED, teeny tiny little purple sphere here. How much flux is there through that purple sphere? Oh my gosh. There's a lot of flux. There's a light bulb inside of it. It's shooting out lots and lots of light, every photon of which goes out of the surface, none of which ever come back into the surface. So tremendous amount of flux in a teeny tiny little bit of volume. So flux per unit volume, very large. That make sense to everybody? Okay. So what I like about this example, I'll call it a sort of a manifestation of divergence and flux, and just sort of a nice little example, intuitively satisfying, relatable kind of physical scenario. What I like about it is it really supports what I've told you all before, this idea that don't fall for the illusion that flux happens on the boundary. That's just where you notice it. Flux comes from the interior. Case in point here, right? If you were to compute the flux on this outer sphere here, yeah, that's a lot of flux. Where is the flux coming from? The flux consists of flowing photons. They came from the bulb, right? And divergence is the thing that points right to where that flux actually came from. Everybody buy it? So I think it's a nice example to kind of chew on. It really does conjure the right image. Okay. Next example. Now this one is a very different kind of a fluid. I'm going to suppose that I have some sort of a gas. It doesn't matter. It could be air. Why not air? Let's do air. We have I'm going to say we have a balloon. Let me draw the balloon on here. The balloon is a nice big red balloon like so. And the balloon, I'm going to suppose, is expanding outward. There's various different reasons, I suppose, that a balloon might be expanding outward. I do want it to be a closed balloon, though. Nobody's inflating this balloon. The total amount of gas actually in the balloon, constant. Fixed amount of air in the balloon. But maybe somebody's heating up the air in the balloon, and of course when gas gets heated it expands. Or maybe somebody's just grabbed on to every point on the side of the balloon and is literally pulling it outwards. Take a pick, doesn't matter, whatever. I appeal to your sense of geometry and physical intuition that if the balloon is expanding, all of the air inside of it is moving kind of somewhat outward along with it. And of course, the pieces of air that are right next to the balloon they're moving kind of as fast as the balloon is. The pieces of air that are right at the middle of the balloon are actually going to kind of stay put, right? Because it's in the middle and it's being pulled sort of equally in all directions. And then, halfway from the middle to the edge is going to be something kind of in between. And I claim that you can describe this vector field like so, and I'll be able to give you somewhat of a justification of that in a couple of seconds. But so again, here we go. We have a red balloon that's expanding, and the air flows like that. Does everybody see my scenario? Right. Okay. Well, now we're going to talk about this sphere here. on that sphere. We can talk about how much flux there is going through that sphere. You can see that some of the air, like looking at that sphere, some of the air is literally passing outward through my fixed purple sphere. Right? As the balloon expands, this fixed purple sphere, the air is moving outward. We can talk about it as flux. It's a boundary. Flux through a boundary can be understood with the divergence theorem. You could straight up compute the divergence of this vector field. Here it is. The vector field F is kx. By the way, a nice little easy little practice problem. But you want to make sure that you can do this even though the vector field is written in vector form. And the formula for divergence is written in terms of coordinates. You can take this vector form and just write out the coordinates. Right? And if you take this vector form of the vector field, write it in coordinates, compute the divergence, I claim what you're going to get is that the divergence is 3k. Nice little exercise. Make sure you can do that. Make sure you get this as your answer. Is everybody with me? All right. So what does the divergence represent in this scenario, right? What does this mean? Well, we've got a flux through this purple surface. Air is leaving the interior. It's leaving out through this purple surface. The flux is telling you how much air is leaving, right? It's the rate that mass of air is leaving out of the purple surface. What is this integral over here? Why would I view the rate that mass is leaving as a triple integral? Well, I'm going to interpret here that the integrand is telling me, and keep in mind, flux happens on boundaries, but it actually happens in the interior. You see it on the boundary, but it actually happens in the interior. Flux leaving through the boundary means there's less total mass on the inside. If there's less total mass on the inside, the overall density has to be decreasing. This integral is counting up grand total how much mass are we losing by looking at every little piece of the interior and asking how fast is the density going down at every location in the interior, and then integrating to get, again, the total rate that fluid is leaving the purple surface. So what we have here, then, this 3K, what the divergence is representing here. Let's see here, green, yeah. Divergence is representing what's the rate of change of air density everywhere inside of this purple surface. And now, again, physical appeal. When you have a balloon, the density of air on the inside, it's always uniform. Right? It would be weird to have a balloon where there's a lot more air on the left side and a lot less air on the right side. Gases just don't do that. Right? The density is going to be constant. So as you expand the balloon, the density is going down at a constant rate everywhere. This being constant is the indication that the density is decreasing at the same rate everywhere. So, different physical scenario, different interpretation of divergence. Now I have a supplemental, this. I'm not going to have any test questions that are going to be on this, but I think this is a nice way to unify the two examples that we've just seen. I'll point out in this first example, we are creating photons. That's what light bulbs do. Light bulbs do not come packed with a certain number of pre-existing photons. There is no photon tank inside of a light bulb, right? It's literally making them. But the density is constant. If you we have light bulbs on in this room, right? The number of photons right in this general area right here, it's not changing. It's a steady state situation. Okay, the exact opposite is what's happening here. In this example, we're not making air. There's no air being created like photons were. But on the other hand, the density is not constant. in this example, right? So these are physically very different kinds of fluids in terms of how they behave, how they exist in the world. So there are some cases, some kinds of fluids where both of these happen at the same time. And it's a little bit weird to try to imagine, but I'm going to make the observation that if you have some region, let's see here, let me, we'll do this with a green, yeah. You have some region, and let's suppose that to some extent or another, there is a creation of fluid. Fluid is being generated on the inside of this three-dimensional region. And if fluid is being generated, I claim there's really only two things that can happen when fluid is generated. One possibility is, and by the way, forgive me for the bad drawing here, but I'm going to draw an arrow coming sort of straight down to indicate that fluid is being created in here. I don't know how else to draw that, right? But if there's fluid that's being created into this it's possible that it could leave through the boundary, thus creating flux. That's one possibility. Another possibility is that if fluid is being created, it could stay. And if you think about it, if fluid is being created and then is staying within the region, that increases the total amount of mass of fluid in the region, which is dm dt. So when fluid is generated, it either leaves and becomes flux, or it doesn't leave and it contributes to dm dt. And now if you just take everything that I have on this equation and just divide by volume, so let's see here, I guess I'll use yellow for this. So differentially per unit volume. So flux per unit volume is divergence. Mass per unit volume is density. Right? And what happens over here is a little, we don't have a pre-existing idea, a pre-existing concept for what I'm calling generation rate density, but how much fluid per unit time is being created in a given vicinity per unit volume. If you kind of think about it, it makes sense, but it's not something we have a pre-existing notion of. The point is, this unifies our initial two examples as follows. If you know for sure that nothing's being generated, if there is zero generation, right, then, and you ask, well, what is my physical interpretation of flux? Well, flux is clearly going to be the negative of the rate of change of density. So divergence will represent the rate that local density is decreasing. Kind of like in the balloon example. On the other hand, let's suppose that I know that there is the fluid's being generated, but there is no kind of like in the light bulb example. There's no change in density. So density constant. Right? If the density is constant, then these are zero. Right? Flux is telling you then very simply how fast fluid is being created. How many photons are being created? Or how many photons are passing out of my bulb is how many photons are being created. Right? So that's the connection to the light bulb example. So when you have a fluid that is a little bit of both, you just have to connect them by way of this formula. Now, anyway, again, you're not going to be tested on that stuff. I just wanted to show you that these two physical scenarios we saw are kind of two extremes of a spectrum of different actual scenarios. Okay. All right, let's talk about gravitational fields. This is one of the big uses of the divergence theorem. Well-known formula for the gravitational field. This right here. Right, we talked about this back in chapter 3. And again, as in chapter 3, this is what we call an inverse square radial vector field because of this being inverse square and that unit vector being radially outward. So, gravitational fields are inverse square radial. By the way, going back to the photon example, you may recall I mentioned that I'd talk about this vector field representing that flow of a fluid. Inverse square radial. Just like a gravitational field is, as it turns out. Right? So that's a heck of a coincidence. Very convenient coincidence. So the vector field describing photon flow and the vector field describing this seemingly static thing called gravity, right? Gravitational field of the Earth, it just kind of sits there. There's nothing actually moving that we perceive anyway. But mathematically, they look just alike. And when two things look just alike, you can pretend that they are the same. And so this is a very common choice in physics because this is the exact same vector field as a flow of fluid created by some particle-emitting stuff. Physicists like to pretend that this is actually a flow of little particles. These little particles, imaginary, possibly real. I mean, there are speculations that they might actually be real. Long conversation ensues about that. We don't actually care about. Whether they exist or not, we can certainly pretend that they exist, and thinking of gravity as being a flow of little photon-like particles called gravitons gives us the exact same formula for the gravitational field. If we pretend that this is true, we will get all the right answers in understanding gravitational fields. So, neat fact. And I'm a big fan. I love thinking about gravitational fields in terms of gravitons. Okay. So, now with that point of view in mind, here's... this is actually 3 equations that are going to imply a 4th equation. We're going to argue kind of like this. So let me take sort of one step at a time here. This top equation is actually no big deal. It looks scary, but if you just kind of ignore the fact that there's this constant on both sides of the equation, that's easily ignored, right? What the rest of the equation just says is mass is a triple integral of density times dV. That's old news. That's one of our very first ideas of triple integrals. Mass is a triple integral of density. And then it's perfectly legal to multiply both sides by any constant you like. I like this constant. You'll see why in a second. Okay, so that's that top equation. Now let's talk about this side equation here. What's going on there? We have to kind of, again, think through the physical scenario here. We've got some mass on the inside of a fixed sphere. Mass creates gravitons. And if I want to ask, what is this total flux of gravitons through this outer sphere? Right, what is the grand total flux? How many of the how many of the gravitons created by the mass actually flow out? All of them, right? If this little piece of mass shoots out a graviton, it 100% will go out through the surface. That's just right. It's just like a photon. They all go out. So the more mass you have, the more flux you're going to have. twice as much mass, twice as much gravitons being created, twice as much flux. Right? So mass and gravitational flux, using this graviton metaphor, mass and gravitational flux need to be proportional. Right? It's actually a pretty deep observation that becomes intuitively satisfying with this little potentially fictional metaphor of graviton. And so you can do a computation, and again, details. And it's a healthy exercise, but we don't have time to do it in class here. You can determine what the actual relationship is here, and it turns out that the appropriate constant to fit in here is this negative 4 pi g, and that's why I wanted to put that on both sides of this top equation. Okay. All right. So we understand this equation. We understand this equation, and this equation down here is just the divergence theorem, right? Flux is a triple integral of divergence. So altogether, the big conclusion then is very simply that if these two integrals are always the same, no matter what solid you're triple integrating over, if these two integrals are always the same, it must be that the integrands themselves must be the same. And so the big idea then is, again, divergence points to where the stuff comes from. Divergence points to where the flux comes from. Flux comes from gravitons. Gravitons come from mass. So divergence points to where the flux, a.k.a. gravitons, a.k.a. mass, comes from. Right? So really powerful conclusion and computationally insane if you don't use the graviton metaphor. The divergence of this gravitational field, the divergence of this gravitational field is proportional to mass density. And it is a bonkers difficult calculation if you just brute force it. It's intractable. Don't try. But you think about things the right way, and it becomes sort of an immediate consequence of the divergence theorem that gravitational divergence tells you mass density. Really powerful fact. Okay. Now, you may be thinking to yourself, I live on the surface of the Earth where the gravitational field is constant. It's really easy to understand constants, and I have no plans on becoming an astronaut. Do I really need to understand all of this stuff? What does this have to do, practically speaking, with us? Fair point. That said, electric fields, not constant. Electric fields are highly non-constant, right? There's every piece of electronics you have, there's little electric fields inside of there doing all sorts of crazy things. Not constant. Right? If you want to understand electric fields, which is fundamental, right, to being able to do any real, engineering that, if other than, building, push lawnmower, right? If you want to build anything, having electric stuff in there is going to be part of it, and understanding electric fields is going to be part of that. Right? And the beautiful thing about it, they too are inverse square radial, emanating from charge. And so, again, things that mathematically behave the same way, you can pretend are actually the same. And so, just like we did with gravitational fields, you can argue about how total charge is an integral of charge density. You can point out that charge is what creates these little flying particles, and these little flying particles are what makes flux. Yeah, there's a constant of proportionality involved. That's a plug-and-chug, tedious calculation. You don't need to do that, but that's what that constant needs to be. And then you can write down the divergence theorem, and what you get is, again, a really important, really valuable conclusion here, that if you want to understand the divergence of an electric field, and you will in engineering classes, right? The divergence of the electric field is proportional to charge density for this reason. Right? So I like this argument better because it's relatable, because I understand mass. I see mass every day. I'm made out of mass. Gravitational fields, I encounter every day. I have a visceral understanding and experience with them, right? To me, all the objects involved in here are extremely relatable. Not so much with electric fields. You can't see electric fields. People didn't even know electric fields existed until, a couple hundred years ago, right? They're elusive. Charge, again, kind of a weird, creepy, there's a lot of trust that goes on with this idea that I'm just supposed to accept that there exists this stuff called charge, right? And until you actually physically experience it, it's a little bit mysterious. So this thing that you need to understand about electric fields, gravitational fields, gravitational divergence, etc., are the perfect physical analog. Independent of whether you're going to be an astronaut, this is a way of helping you to understand electric fields. And I'm sorry, I'm out of time. So we'll draw the line right there. Y'all have good rest of your Wednesday. See you on Friday. And as usual, make sure I mark you as present for attendance.